Look at this result. 3 properties, 3 green pass labels, and no counterexample. If we stopped here, we might say the arbiter has been formally verified. Now look at the waveform. Request never becomes 1, not once. The property that says every request receives a grant passes because the environment has quietly forbidden every request. The hidden assumption is that request always stays low. So did we prove the arbiter, or did we prove that nothing happens when nothing happens? That is the problem we are going to solve in this lesson. A formal proof can be mathematically correct and still answer the wrong engineering question if we define the legal environment incorrectly. In the previous lessons, we built properties that describe what a design must do, but a formal engine also needs to know what the world around that design is allowed to do. When we verify one block, we normally do not include the complete chip around it. Inputs arrive from logic that is outside our proof scope. From the formal engine's point of view, those inputs are free unless we restrict them. They can take any values allowed by the model at each sampled step. That freedom is powerful because it lets formal explore combinations we may never think to write as tests. It is also dangerous because the engine does not know which combinations violate the real interface contract. Constraints define that boundary. They tell the formal model which environmental behaviors are legal for this verification task. But I want to be precise. An assumption is not a command that makes the design correct. It is a condition under which we ask the tool to prove the design. If I assume something the real environment does not guarantee, my proof may be valid only inside an imaginary system. The goal is not to write as many assumptions as possible. The goal is not to make failures disappear. The goal is to describe the legal verification universe closely enough that impossible traffic is removed while every meaningful legal behavior remains available. Think of the outer field as every behavior the encoded model could produce. Reset and the RTL transition logic determine which states and traces are reachable. Each justified assumption removes behavior that the surrounding environment forbids. Assertions identify behavior the DUT is not allowed to produce. Covers ask whether a selected useful behavior can still occur. This lesson is about getting that division right. We will build a request and grant environment step by step. We will see underconstraint where impossible traffic creates distracting failures. We will see overconstraint where a green pass hides the feature we meant to verify. We will examine the special risk of assumptions on internal signals. And we will use covers before assertions to check that our proof environment is alive. The sentence I want you to keep in mind is this. A useful constraint removes behavior the environment truly forbids. A dangerous constraint removes behavior merely because it is inconvenient. Let us use one small interface for the entire lesson. The environment drives request and cancel. The DUT drives grant and busy. After reset, the environment may issue a request. Once the request has been accepted, it should remain asserted until the DUT grants it or the environment cancels it. Cancel is optional in our example, and it cannot occur in the same sample cycle as the initial request. The DUT must never grant without a pending request. For our bounded response requirement, an accepted request that is not cancelled must receive a grant within 1 to 3 cycles. This is not a universal protocol, it is a teaching contract that we are defining explicitly so we can reason about ownership. Notice what we did before writing any SVA. We decided who owns each rule. If the requester is responsible for keeping requests stable, that rule is an assumption when we verify the arbiter. If the arbiter is responsible for granting only a pending request, that rule is an assertion. If I accidentally assume the grant rule, I have removed the very bug the arbiter proof is supposed to find. This ownership question is more important than syntax. Before you write assume property, ask which component is responsible for making this true in the real system. If the answer is the current DUT, it is usually a checker, not an environment assumption. If the answer is an adjacent component, we can model it as an assumption here, but we also need a plan to verify that adjacent component provides the guarantee. This is the core of assume guarantee reasoning. One block is proved under a promise from its environment. Somewhere else, that promise must be checked, justified by architecture, or discharged at integration. we should also write down the source of each promise. Is it in an interface specification? Is it an architecture invariant? Is it an integration restriction? Is it only a temporary simplification for bring up? A sentence from a meeting is not automatically a contract. A signal name is not a contract. The fact that simulation has never violated a behavior is not automatically a contract. For our example, request stability comes from the requester interface contract. We can later check the same rule as an assertion when verifying the requester. Reset usage comes from the reset integration contract. The optional mode restriction, if we add one, comes from our verification staging plan and must eventually be removed. This record matters because formal can backpropagate assumptions through logic. A simple line can remove a surprisingly large part of the behavior space. If we cannot explain who owns an assumption and how it will be validated, we should not quietly treat it as fact. Now that we have responsibility assigned, we can build the environment in the order that makes debugging easiest. Clock, reset, basic reachability, input protocol, then functional properties. Start with the sampled clock. Our properties observe values on the rising edge. That sounds obvious, but an incorrect default clock, an accidental second clock, or logic between clock domains can change the meaning of every temporal relationship we write. For a single clock teaching model, we define one rising edge sampling event and keep all visible properties aligned to it. For a real multi-clock block, we cannot simply pretend the clocks are one. The setup, synchronization assumptions, and supported formal mode need separate review. We are not solving CDC or RDC in this episode. Now reset. In this lesson, reset is active high and asserted initially for two sampled rising edges. After that, it is released. The important point is that formal tools do not infer our intended reset story from a signal called reset. We have to encode initial conditions and legal reset behavior. If we constrain reset too weakly, the engine may explore startup behavior the real system cannot produce. If we constrain it too strongly, we may hide bugs involving reset, release, soft reset, or state that is not actually initialized. Suppose I force every state bit to 0 at time 0 because that makes the proof easy. If the hardware specification resets only some of those bits, I have added a guarantee that silicon may not have. My proof is now about an idealized startup state. That can be a valid temporary bring-up model, but it is not free. I need to label it, show which behavior it removes, and decide how the real initialization condition will be verified. A related mistake is forcing reset low forever after the initial sequence that proves behavior only in a world with no later reset. If our block can receive a warm reset while requests are pending, that scenario requires either inclusion in the proof or an explicit scope statement. This does not mean every property must handle every reset scenario in one run. We can create separate tasks, one for normal post-reset operation, one for reset interruption, and one for reset recovery. What matters is that the split is intentional and the combined verification plan covers the requirement. Wrong polarity is especially deceptive. Some internal values may move during reset, so the environment does not look completely dead. A loose cover may even report activity. But the functional mode we care about is unreachable. That is why our first covers are not complicated protocol goals. We begin with very basic questions. Can reset assert as intended? Can it release? Does an idle functional cycle exist after release? Can a request rise after reset is released? Do not stop at the word covered. Inspect the witness. Confirm the event occurred after the intended reset on the intended clock and in the intended functional mode. A cover reached from garbage reset values is not useful evidence that ordinary traffic works. A cover reached only in scan mode is not useful evidence that functional mode works. The waveform gives the status meaning. So our first constraint rule is simple. Clock and reset setup are not background configuration. They are part of the proposition being proved. Let us translate the request protocol carefully. We will not begin with code. We will begin with a sentence, assign ownership, and test whether normal behavior remains reachable. This is not an assumption that forces a request. It is a reachability expectation. We express it as a cover. We want the environment to allow both idle cycles and request cycles. This is a guarantee made by the requester, which is outside our arbiter proof. Here it becomes an assumption. But even this sentence needs precision. What does accepted mean? Is it simply request hi while the DUT is ready? Is there a separate handshake? Does cancellation end the obligation immediately or on the next sampled edge? Does grant and cancel in the same cycle count as completion? If we do not answer those questions, the property code will answer them for us, often accidentally. For our teaching contract, accepted request is the sampled event that begins the pending state. Once pending is true, request stays high until grant or cancel. Cancel is not allowed in the same sampled cycle as the initial request. We will treat grant as completion on the cycle it is sampled high. Now classify the DUT obligations. Grant without a pending request is an arbiter error, so that is an assertion. Grant within 1 to 3 cycles after an accepted and non-cancelled request is also an assertion. The environment must not be allowed to assume either of those outcomes. This kind of mistake happens when we use assumptions to make a liveness or response proof converge. If I assume the output I am supposed to prove, I have converted the requirement into a premise. There are legitimate cases where an output is controlled by the environment because our module boundary is unusual. That is why signal direction alone is not enough. Ownership comes from architecture, but for this arbiter, grant belongs to the DUT. This environment rule should also be as narrow as the contract. We should not forbid cancellation entirely just because cancellation creates more cases. If cancellation is in scope, we must allow it and cover it. If cancellation is intentionally out of scope for the first bring up stage, we label that restriction as temporary. The covers serve a different purpose from the assumptions. The assumption says which traces are legal. The cover asks whether a representative trace still exists after all our assumptions interact. This interaction matters. Two individually reasonable assumptions can contradict each other. A reset assumption and a mode assumption can combine to block traffic. A stability assumption may begin one cycle too early and prevent the request from ever rising. Looking at each line in isolation is not enough. After adding each assumption, rerun the small cover ladder. This gives us a local answer to an important question. What behavior did this line remove? If a request was reachable before the new assumption and unreachable after it, we have a precise place to debug. We do not have to wait until 30 assertions all pass suspiciously. That is why formal environment bring up should be incremental. One contract statement, one assumption, one set of covers, one waveform review. We are building an executable boundary, not dumping a list of restrictions into a file. Before trusting assertion results, I want evidence that the environment can perform ordinary useful work. First, cover reset release. Second, cover at least one normal idle cycle after reset. Third, cover request becoming active. Fourth, cover the request remaining pending. Fifth, cover a completed request and grant. Sixth, cover a second separate transaction. If cancellation is in scope, cover a cancellation path too. Why start with covers instead of assertions? Because an assertion can pass when its triggering behavior never occurs. A cover forces us to ask whether that behavior is possible under the current assumptions and setup. But covers have limits. A cover that request can rise does not prove grant logic is correct. A cover that one transaction completes does not prove every request completes. Covers are reachability evidence, not universal correctness. Also distinguish a completed cover from one whose target was not found. In a bounded cover task, the tool may search only a selected number of cycles. If the target is not found, the honest statement may be, this cover was not reached within the current depth. That is not always the same as proving the target unreachable. So when a cover does not complete, ask what kind of result you actually have. Did the engine prove unreachability? Did it stop at a finite bound? Did it time out? Did the cover syntax fail to compile? Did another assertion terminate the task? The status and mode matter. Open a cover witness where request rises only during reset. Now inspect witness quality. This cover technically reaches request high, but it reaches it while reset is active. That does not demonstrate legal post-reset traffic. We repair the cover by including the intended functional context or by writing a second cover that reaches request after reset release. Then we examine the new waveform. The same rule applies to more complicated designs. If we cover a queue becoming non-empty, check whether it happened through an ordinary enqueue, not because an uninitialized count woke up non-zero. If we cover a transaction, check that it happened in functional mode rather than scan or test mode. If we cover an interrupt, check that the triggering event is realistic. A good cover set represents typical valid behavior, not only exotic endpoints. We want enough coverage witnesses to recognize whether the proof space resembles the system we intended. For our request and grant example, the cover ladder also helps locate mistakes. If reset release is covered but request is not, inspect request constraints. If request is covered but pending is not, inspect acceptance and stability. If pending is covered but grant is not, inspect the DUT, response property bound and cancellation behavior. Turn the ladder into a diagnostic tree. This is a more reliable bring-up workflow than starting with 50 assertions and celebrating whatever turns green. We establish life first, then safety and response obligations, then richer combinations. Covers first does not mean covers only. It means we verify that meaningful traffic is present before interpreting universal proof results over that traffic. Now we deliberately leave out the stability rule for the request signal. The formal input is free to rise for one cycle and fall immediately, even though our interface contract says a requester holds it until grant or cancel. The response property fails. The waveform shows request rising, the arbiter capturing a pending operation, request disappearing, and internal control reaching a state the real requester should never create. This is under constraint. Our model admits behavior the real environment forbids. But do not rush to add an assumption simply because the trace looks strange. We first classify it. Is the trace legal according to the written contract? Who owns the surprising signal? Are clock and reset correct? Is the checker sampling the intended cycle? Can the real adjacent block produce this sequence? If the request pulse is legal, the DUT or property must handle it. Adding an assumption would hide a real requirement. If the request pulse is illegal and the requester guarantees stability, then the narrow stability assumption is appropriate here. We should also verify that guarantee when we verify the requester or at integration. The unrealistic pulse disappears, but request, pending, grant, and cancellation remain reachable. This is what a healthy assumption change looks like. It removes the documented illegal behavior without killing the feature. Under constraint usually produces false failures and extra debug work. It can also make proofs harder because the engine explores unrealistic combinations. Still, under constraint is often safer than over constraint during early bring up. A red trace forces us to ask a question. A bad green result may never attract attention. That is why I prefer to begin with fewer assumptions, classify counterexamples, and add only constraints justified by the interface contract. Each new assumption should answer a specific illegal trace, not a general desire for green results. There is another subtle point. Formal input behavior is not random traffic in the simulation sense. The solver selects values that satisfy assumptions and reach a target or violation. If our assumptions permit a pathological sequence, the solver is allowed to use it immediately. So, when formal finds a bizarre corner, our job is not to complain that no test would generate it. Our job is to decide whether architecture permits it. The contract wins if the behavior is legal, fix the design or checker. If the behavior is illegal, encode the smallest correct environmental guarantee and prove that it is supplied somewhere. Now let us make the opposite mistake. We add an assumption that request is always low after reset. The response assertion passes, no grant without request property passes, busy behavior passes, the dashboard becomes beautifully green. Then we run the request cover. It is not reached, we inspect the model, and the reason is obvious, we prohibited the trigger. This is over constraint. We removed behavior that belongs in the intended verification space. At the property level, the response implication is vacuous because accepted request never occurs. No response obligation starts. At the feature level, this is partial vacuity. The design may still leave, reset, toggle status bits, enter idle states, and satisfy unrelated properties. The entire proof space is not empty, so a simple null environment check may not flag the real problem. The request feature is what disappeared. That distinction matters. Automated vacuity checks can detect many contradictions and unreachable triggers, depending on tool and property form. They are valuable, but they cannot replace covers designed around our feature intent. Now request is reachable. The transaction cover produces a normal witness, and the response assertion fails because one request waits 4 cycles, even though our requirement says 1 to 3. The first pass was not a lie from the formal engine. It correctly proved the property for every trace allowed by the bad environment. We asked the wrong question. Repair the illustrative response behavior and rerun both proof and cover tasks. After the DUT fix, the assertion passes for the selected scope. The request trigger is covered. A complete transaction is covered. A second transaction is covered. We inspect each witness and confirm it occurs after reset in functional mode. This is much stronger evidence than the original green badge because we have checked both sides of the verification question. Can any legal execution violate the rule? And can representative legal executions actually exercise the rule? Neither answer replaces the other. A cover witness demonstrates existence, a proof demonstrates absence of a violation within its stated scope and assumptions. Together, plus review of the model and properties, they make the result meaningful. In full vacuity, contradictory assumptions remove every legal trace. Many tools can identify this directly. In partial vacuity, the model still has legal behavior, but an important operation is excluded. This is harder because the environment looks alive. We detect it by covering each expected feature, reviewing witness quality, and tracking what every assumption removes. The practical warning is simple. Never measure environment quality by assertion pass rate. A completely dead feature can produce excellent pass statistics. Measure it by intent. Are legal transactions reachable? Are important modes present? Are the assumptions independently justified? Did the tool return a conclusive result? Did we inspect the traces? So far, our assumptions have been on primary inputs. Formal tools also allow assumptions on internal signals, and that can be useful. Suppose an internal decoder combines opcode, mode, and request fields into rec valid. Writing accurate input assumptions for every encoding may be cumbersome. We could instead assume that rec valid has only legal behavior and focus the proof on downstream arbitration. Unlike a simple simulation force, a formal assumption participates in the mathematical model. It can restrict combinations in both its fan-in and fan-out. The solver keeps only traces consistent with the assumed internal condition. That convenience has a cost if the decoder itself produces an illegal rec valid value for a legal input. Our internal assumption may remove exactly that bug from the proof. We have effectively said, for this verification task, treat the decoder output as correct. That can be acceptable if our scope is intentionally downstream and the decoder is independently verified. It can also be useful as a temporary abstraction or complexity reduction. But we must not describe the resulting proof as covering the decoder. Shade the decoder as excluded from responsibility and attach a verification owner. Whenever you assume an internal signal, ask 5 questions. First, what logic am I excluding from responsibility? Second, where is that logic verified? Third, is this a temporary staging assumption, a contractual abstraction, or a permanent proof boundary? Fourth, can realistic upstream activity still reach the downstream behavior I care about? Fifth, how will this assumption be documented and reviewed so it does not silently survive beyond its intended scope? The same caution applies to black boxes and cut points, which we will discuss more in the complexity episode. Once an internal relationship is replaced by a free value plus assumptions, the validity of those assumptions becomes part of the proof claim. A clean assume guarantee split can be powerful. The decoder task proves the internal signal obeys its contract. The arbiter task assumes that contract and proves downstream behavior. Integration checks that the same versions and configurations are connected. But if the decoder proof does not exist, the arbiter proof has an open dependency. We should label that dependency rather than allowing a green result to imply complete verification. At this point, it may sound as if every overconstraint is forbidden. That is not the right conclusion. During early design exercise, intentional overconstraint can make a large environment understandable. We might disable low power mode, restrict transaction types, hold error injection inactive, or reduce a data bus to a smaller active subset. The difference is management and scope. In stage 1, we enable one normal transaction and prove basic safety. In stage 2, we add cancellation and more opcodes. In stage 3, we restore optional modes and broader data behavior. Each temporary assumption has a clear name, owner, reason, affected features, and removal or discharge plan. We do not call stage 1 a complete proof of the full interface. We call it a scoped bring-up result. A useful naming convention can make temporary assumptions easy to audit, for example, an fvstab prefix. The exact prefix is less important than a rule that every such assumption appears in a review report. After each assumption is removed, rerun the cover ladder and the affected assertions. The proof space has grown, so old results do not automatically apply. Sometimes an intentional restriction remains permanently because another proof, architecture rule, or integration check discharges it. That is also acceptable when the connection is explicit. What is dangerous is not simplification itself, it is forgotten simplification presented as universal confidence. Here is the review workflow I want us to use. For every assumption, record its plain language meaning. Record who owns the guarantee. Link it to a specification, architecture decision, adjacent checker, or temporary staging plan. Describe the behavior it removes. Name at least one cover that checks expected traffic, remains, state how the assumption will be discharged. Then challenge the environment in 4 ways. First, lint the assertion and assumption code. Lint can catch suspicious syntax, unconditional sequences, clocking mistakes, and other structural problems supported by the rule set. Second, review the properties and assumptions with someone who understands both SVA and the interface. Translate every line back into plain language. If the translation does not match the requirement, the code does not get approved. Third, include formal assumptions as checks in available simulation or integration environments when practical. Simulation explores less behavior, but it drives realistic system flows and can reveal that an adjacent block violates a supposed guarantee. Fourth, inspect covers and witness waveforms. Confirm that ordinary transactions, modes, and repeated operations remain possible. No single layer is sufficient. Lint does not know our intent. Peer review can miss an interaction. Simulation samples behavior rather than proving the assumption universally. Covers demonstrate selected reachability, but not every legal path. Together, these layers make silent overconstraint much harder. Also record the formal result accurately. A bounded pass is not an unbounded proof. A timeout is not a failure. A cover not reached within depth 20 is not automatically a proof of impossibility. An induction failure trace is not automatically a reset reachable counter example. The result label is part of technical honesty. Before sign-off, review assumptions as aggressively as assertions. We naturally focus on what the DUT must do, but assumptions define which DUT behavior we were willing to consider. A mistake there changes the question before the solver begins. Before we recap, let us perform one complete constraint audit as if this environment had arrived in a code review. We begin with no protocol assumptions beyond the clock and the initial reset sequence. Request and cancel are symbolic environment inputs. The first request cover succeeds, so traffic is possible. The response assertion fails on a one-cycle request pulse. Our first question is not, how do I make this pass? Our first question is, does the interface contract allow the pulse? The requester owns that guarantee and the written contract forbids the pulse. We add the narrow hold while pending assumption. We also add the same rule to the requester's verification plan as an assertion because our arbiter proof cannot establish that the requester really provides it. Now rerun the cover ladder, reset releases, request rises, pending lasts for multiple cycles, grant completes a transaction, cancellation remains reachable. The assumption removed the illegal pulse without deleting normal traffic. Next, Another failure appears. Cancel rises in the same cycle as the initial request, and our checker does not know whether an obligation ever started. Again, read the contract. In this stitching protocol, simultaneous initial request and cancel is illegal. We add exactly that environmental rule. We do not ban cancel globally because cancel is a real feature. The cancellation cover still succeeds on a later cycle, which is important evidence that we constrain only the ambiguous initial combination. Now suppose the response proof is difficult and someone proposes this shortcut. Assume grant occurs within 3 cycles. That is not an environment guarantee in our architecture. Grant is a DUT output and the deadline is the requirement we are trying to prove. Adding that assumption would turn the conclusion into a premise. We reject it. Then someone proposes, assuming the internal decoded signal accepted request behaves correctly. That may be useful for a downstream only proof, but it changes scope. We ask where the acceptance decoder is verified. If there is a separate proof checker or integration test that establishes the decoder contract, we can record the dependency. If there is no such evidence, the downstream pass cannot be presented as verification of the decoder. Next, inspect reset. The setup asserts reset for 2 rising edges and then forces it low forever. Our normal operation task may intentionally use that restriction, but the architecture also permits a warm reset. We therefore do not quietly broaden the claim. We label the current task post-startup normal operation and create a separate reset interruption task in the verification plan. The 2 tasks have different covers and different obligations. Finally, inspect the status dashboard. The request to grant assertion is proven in the selected scope. The trigger cover is reached after reset. A complete transaction is reached. A cancellation path is reached. A second request is reached. Temporary staging assumptions are either removed or listed with owners and discharge plans. Only now do we summarize the result. We do not say the arbiter is universally correct. We make a narrower claim for this RTL revision and configuration. The selected properties are proven under the reviewed requester and reset contracts. We also have reachability evidence for representative request, grant, cancellation, and repeated transaction behavior. Warm reset behavior remains covered by a separate task. That sentence is longer than pass, but it is also honest. It tells another engineer what may be reused, what must be rechecked, and where confidence still depends on external evidence. Use that loop every time a counterexample suggests a new assumption. Classify the trace, justify the environmental rule, constrain only the illegal behavior, run the reachability covers again, run the affected proofs again. Record the resulting scope and dependency. If any one of those steps is missing, a local fix can become a hidden verification gap. One final habit makes this workflow easier to maintain. Keep assumptions close to the interface boundary and organize them by purpose. Separate reset assumptions, protocol assumptions, temporary staging assumptions, and abstraction assumptions. When a proof changes, review the category that changed and rerun the covers connected to it. Do not leave an unlabeled pile of constraints where a reviewer cannot tell which lines are architectural and which lines were added during debug. Treat removal as a planned operation. A temporary assumption should have a condition for deletion, not merely a comment saying temporary. For example, remove this opcode restriction after the basic request, cancellation, and repeated transaction covers pass. That condition lets the team know when the proof space should expand. And keep the environment versioned with the RTL and checkers. A proof result cannot be reproduced from the property file alone. The assumption set, tool setup parameters, and exact design revision are all part of the artifact. Let us close with the complete picture. Formal explores the RTL model under its clocks, reset setup, assumptions, properties, parameters, and tool configuration. Underconstraint admits behavior the real environment forbids. It often produces unrealistic counterexamples and wasted debug effort. We fix it only after confirming the behavior is truly illegal and owned by the environment. Overconstraint removes behavior that should remain legal. It can make properties pass without exercising the feature. We detect it with trigger covers, transaction covers, witness review, assumption review, and available vacuity checks. Internal assumptions can simplify a downstream proof, but they exclude responsibility for the logic that generates the assumed signal. That excluded logic needs an independent verification story. Intentional overconstraint can help stage bring up when it is named, scoped, reviewed, and later removed or discharged. And covers first does not mean covers replace assertions. It means we establish that expected behavior is alive before trusting universal proof results over that behavior. Here is the one-line rule. A useful constraint removes behavior the environment truly forbids. A dangerous constraint removes behavior merely because it is inconvenient. In the next part, we will go one step deeper. We will take the suspicious green pass from this lesson and triage it properly. We will separate base case failures from induction traces. Then we will examine weak properties and vacuity and repair a proof that was passing for the wrong reason. A pass is useful only when we understand what was proved, under which assumptions, and whether the behavior we care about was actually reachable. If this lesson helped you review constraints more carefully, like the video and share it with another verification engineer. Subscribe for part 5 where we will debug counterexamples, weak properties, and vacuous passes.